last night.
All right. Excuse me. Let me get started. I will begin with a word of prayer. I'm going to try anyway. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students, and we thank you for the small amount of snow here in town today. And I just ask you to be with us, help us to glorify you again, Lord, in what we do. In your name I pray, Lord Jesus. Amen. You guys got any questions? Yes, sir. Can we do a what? A hyperbolic trig substitution. Sure. Let me think about this. Example. Let's try to do something like, I don't know. Let's go for like I may regret this, x squared over the square root of x squared plus 1 dx. Maybe we can do a hyperbolic trig substitution on that one. I reserve the right to change that x squared to a more convenient power as to make this example, not take too long. But we'll try it. All right, so the key idea is just to know your identities, yeah? So cosh squared phi minus sinh squared phi is equal to 1, which tells me that cosh squared phi is equal to 1 plus sinh squared phi, right? So that's kind of the identity that I'm anchoring my substitution on. What I'm going to do, and do you want me to make it harder? No, I'll make it harder. Let's make this 4 there. All right. Not too hideous, but slightly more hideous. 4. So in view of that, I'm going to let x equals to twice hyperbolic sine of this angle phi. And so then my dx, you got yourself a 2 cosh phi d phi. And your, x squared plus 4, that's going to give you 4 sinh squared phi plus 4, factor the 4 out, and you got yourself a 4 cosh squared phi, which is kind of the point here. So in view of that algebra, this becomes the integral of 2 times the hyperbolic sine of phi. Square that thing, that's just x. My dx, my dx is, what you got? 2 cosh phi d phi. And then downstairs we got the square root of 4 cosh squared phi. I guess I'm content with my my square here. It's not too bad. But you know what? I'm discontent. I've grown discontent with the square. Let's change that square upstairs. Let's make it a cube. That'll be more fun. Cube. Change the 2 to a 3. Add 1. So third power. Because that's going to make the integral a little bit more interesting for us. Because I don't think we've done one quite like this. So that gives me the 2 cosh phi. Listen, guys, what happens here is this cancels that, right? Those are the same. 2 cosh phi, both above and below. So what you're left with then is 8 hyperbolic sine cubed phi d phi. How do we do that integral? See, with the square there, we'd have had to integrate hyperbolic sine squared. And we could have done that. We just put in e to the phi minus e to the minus phi divided by 2, square it. We've done one kind of like that before. This one, I don't know if we could run up against this yet. But the same trick that we usually do works. So this is what? This is integral of 8 sinh squared phi, right, times sinh phi d phi. And then what do? I can trade a sinh squared for a what? See, sinh squared phi is what? It is cosh squared phi minus 1, yeah? So I can trade my sinh squared for cos squared minus 1. And why would I do that? Do you guys see why I do that? So they're the people in here who have confidently understood how to integrate odd powers of sine and cosine, all right? You need to count yourself among that group of people before the test. Those will come up. Like integral of sine cubed is not hard. It's an inevitability in calculus 2, all right? It will happen. Integral of cosine cubed, not hard. And integral of any odd power of hyperbolic sine or cosine, also not hard, because you peel off one power, it leaves you with an even power, and then you can rewrite that even power as a square of the other hyperbolic function. Sometimes you have to FOIL it out. Like if I had the 5th power instead of a cube here, I'd have to square this, right? But it's not a big deal, because then you let u equal cos phi. And so what we're up against here is 8 u squared minus 1 du, right? Which then you can integrate. So that gives us 8/3 u cubed minus 8u plus a constant, which is 8/3, what was my u? Cos cubed phi, right? Yeah. Minus 8 cos phi plus a constant, all right? Now in my notes, I provided for you this, and this is something I haven't projected yet, but maybe I should. Here, let me project this because it'll take me too long to write it out. If I can find this thing. So we're in integration techniques right now, right? And I think well, it's not at the very end, but it's like before the partial fractions. I think it's right before partial fractions in there. Let's see here. So I start, come on. You can do it. You can do it. There we go. For full context, whenever I say you can do it, I'm thinking of that Olympic coach who praised the little girl for running with a half-broken ankle to fully break her ankle, jumping over this stupid thing to jump on her almost half-broken, then fully broken ankle. And we all were like, yay, a grown man made a girl break her foot in front of thousands of people. It's wonderful. It's heroic. I don't know, kind of child abuse. But but then again, I don't have this like deep-seated love of sports like so many people do. So whatever. If you don't know what I'm talking about, it's probably because it's from before you were born. Sorry about that. But anyway, so at the start of the implicit, no, see, I probably should edit that out. Oh well, but so this is implicit substitutions. At the start of this, I wrote this at the start of implicit substitution for us on the board right over there. I wrote all these. So here's the trigonometric substitution, the triangle for each, right? But then, at the very end, I do the same, but I make these hyperbolic triangles. And so the reason I make these hyperbolic triangles is so that you understand that they don't satisfy the Pythagorean theorem. You don't have a squared plus b squared equals to c squared. That ain't the case for these triangles, because they're not flat triangles. They're hyperbolic triangles. And anyway, so like which one are we doing? Sinh, x equals sinh, where is that? Oh, that's this one, number 2. So my triangle for this substitution is this. Let's see here. So what's my let's see here. I've got what? X. My R is, in this case, 2, right? And I've got square root of x squared plus 4 down here. The hyperbolic angles in there. And so in view of this, cos phi, in fact, you can work it out, is square root of x squared plus 4 divided by 2. And so in terms of algebraic functions, here it is. 8/3 square root of x squared plus 4 over 2 quantity cubed minus 8 times quantity x squared of x squared plus 4 over 2 plus a constant. Now listen, this triangle is just a way to remember the relation between cos sinh and the substitution. You can derive these things from algebra alone, which is how I would have often done it in previous semesters. Like how would you derive cos phi is equal to this here if you don't know about my magical pulled from the air triangle that I haven't really proved to you guys? It's not complicated. All you do, if you don't remember the triangle, is you write down what you have, which is what? X equals 2 sinh theta, right? And then what do? I mean phi. You know that cos squared, well, cos phi is what? It's equal to the square root of 1 plus sinh squared phi, yeah? By this? How do I know I don't need a minus? How do I know it's plus? Remember what cos phi looks like? You guys remember the graph of cos? It's like this. Its lowest point is 1. It's exponential on both sides. This is the graph of cos. All right? So it's not negative. Better than that. In fact, hyperbolic cosine is always larger than 1. Its smallest value is 1 at 0. So I can justifiably choose the square root, the plus square root here, of course, and that makes sense. But what is sinh phi? Sinh phi is x over 2 quantity squared, right? I mean, I'm squaring sinh. And then if you look at that, well, that's the square root of x squared plus 4 divided by 2. Which, of course, is what I said before on the basis of my magical hyperbolic triangle. If you're wondering, there is a whole theory of hyperbolic trigonometry, which you're not taught, and certainly elementary school teachers and middle school teachers don't know, unless they had the good fortune of studying this. There's a book by Saul Stahl that has like all of your favorite theorems from trigonometry, you know, with sine and cosine. There are analogous theorems for hyperbolic sine, hyperbolic cosine, where the angles, where the triangles no longer have a sum of angles which is 180 degrees. In fact, the sum of the angles in a hyperbolic triangle is less than 180 degrees. And also it's not fixed either. It depends on the area of the hyperbolic triangle and so forth. So when you're not in flat space and you start talking about triangles, it's much more interesting. Yeah, there was a question. Yes, sir?
Should we be able to derive this for the test?
You should be able to do this. So yeah, you should be able to do that because you don't have to do this. You could do this. So, right? Like you don't, this is just a help. You don't have to memorize this if you don't want to, because what we did over here is just algebra. So now the larger question is, do you have to do a hyperbolic substitution for this one, right? You could also go with a trig substitution. Where that would have taken you? Where would that have taken you? Well, would it have been a tangent? I think this is a tangent substitution, right? 2 tangent. And then 2 tangent would have given me a secant squared, 4 secant squared, and the square root. The derivative of tangent would have been a secant squared. So I think, by my estimation, we would have had secant times tangent cubed. This problem is also easy in trig substitution. This one's easy either way you go. So I don't usually, I mean, there are problems, it kind of depends. There may be a problem where I said, please use a hyperbolic substitution to do it. But unless I say that, you don't have to do it. Like you could use trig or you could use hyperbolic depending on your...
For the test where you might say that, or is that something that will be prepared?
Well, yeah, I mean, that's part of the class. There's a problem like that in the homework. So generally speaking, the homework kind of shows you more or less what I'm thinking about. Now, there are exceptions to that. Like I would say that the Weierstrass problem in the homework, that's harder. That's not really a reasonable test question. It's a reasonable bonus test question, but not, you know, I once put the Weierstrass substitution unannounced on a Calculus 2 test, and when the student solved it the same way I did, to the point I did, that gave me something to write him in a reference letter, right? So there's that. So I do put hard things on Calculus 2 tests because I'm looking for somebody to, if they have the ability to do it, so then I can write them a letter of reference later or something. Like, it gives me something to talk about later for students. And in the meantime, everybody who doesn't get it, there's no shame in it. It's just a bonus question, right? So this starts to fall in that category, right? So, yeah.
So, for the most part, there's not really a problem where you can't use hyperbolic or trig. Like,
Is there a problem where you can't use hyperbolic or trig?
or there's a problem like where you can only use hyperbolic instead of like.
Well, if I say so, I suppose. But
Well, other than that.
no, you can always go either way. It's just, goodness gracious, sometimes the trig substitution lands you at like secant cubed, whereas the hyperbolic substitution gets you to like a hyperbolic cosine squared. Well, hyperbolic cosine squared is way easier to deal with than secant cubed. But we should be ready to integrate secant cubed, right? That's something you should probably work through. As we've pointed out, it comes up. Other questions? Yeah.
Would there be a way to tell OC to do hyperbolic rather than trig?
Just try it. Situational awareness, you know, the knowledge that if I have, you know, secant tangent times the power of secant, that's harmless because it's just a u substitution. If I have, you know, a tangent or a secant to a power and there's an even power. If I have a tangent or a secant to an even power and I have, you know, like, well, tangent or secant to an even power, that's not bad because I can make a u equals tangent substitution to do those, because derivative of tangent secant squared. So like that's how you know after you've made your initial substitution whether or not that's a path you want to keep going down. You know, if you come up against integral secant to the fifth, maybe you need to rethink whether or not you really want to do that. I don't know. Maybe there's a better way. So, yep.
You were talking about yesterday with the improper evidence, how the denominator is a greater degree than x to the first or something, and it will converge.
Oh yes, let's get back to that. So.
We're feeling confident it was like 1 over lx or something, and it was all in the positive range, like.
Sorry, this thing has rudely talking over you right now. You have to say what you said again. You said something about 1 over natural log, or?
It was 1 over x ln x.
1 over x ln x. So I guess the first issue with 1 over x ln x is how do you integrate it?
Just what they used to because
It diverges. Well, yes, but that's not, when I say a bigger power, that's not a bigger power. X times log x is still in the category of 1 over x. But you're right, that's if you want to look at it, then maybe that's a little, you're arguing that's a little bit past 1 over x. Yeah, you're probably not wrong. I mean, so everybody understands what we're talking about, let's just work that real quick, yeah? So x log x, is that it? And so how do we do this integral? Is it just a u substitution?
Yeah.
Oh yeah, I'm a dummy. I was about to do integration by parts. That would have been dumb. So du dx over x. I mean, that's kind of actually a really important comment I just made, which is don't make things harder than they need to be. That's a lot of it in here. Yeah, I'm teaching you new tricks, right? Integration by parts, partial fractions, trig substitution, hyperbolic substitution. But goodness, don't use those if a u substitution will work. How do you know if a u substitution will work? If you're weak on it, you need to review it, right? Go back and work all those u substitution problems until they're boring. And I mean that in the positive, not college algebra sense of math being boring. Let's see here. So, so anyway. So that's the natural log of the absolute value of u, which is what? Log of log x, right? That's the integral. So if I'm integrating, say, from 1 to infinity, ooh, was it 1 to infinity?
It was e2.
That's good. Why is 1 to infinity problematic here? What would the integral from 1 to infinity of dx? So, I mean, we can make sense of this, yeah? Actually, let's do that. That's a little bit harder problem. What would we mean by that? So here what has to be meant, right, because log of 1 is 0, right? So this is a doubly improper integral. It has to be improper on both sides. See, this would be like the limit as a goes to 0 from the right of the integral from a to, well, let's say e, okay? Dx over x log x plus the limit, let's say t goes to infinity of the integral. And you don't have to use t here. You could use whatever you want, you know? But I'll use t. Dx over x log x. And then what? Well, we did the integral, right? So ftc2, and what's that get us? It gets us a natural log of the natural log of e, all right, minus the natural log of the natural log of a, all right? I should say absolute. It's the natural log of the absolute. Here the absolute value really matters. The first one I didn't need it because the natural log of e is what? Shouldn't need a calculator for this one. It's 1, right? Yeah. And then we've got plus, but you do have a calculator if you forget. I mean, I assume you have a calculator. Limit t goes to infinity of, unpleasant, log of the t. Since we're taking the limit t goes to infinity, I don't need absolute value there. Minus log of e. So the second limit is what you came up against when you were working this problem, right? What's your name?
Sam.
Sam? So that's right. I should know that. So that's basically what you were coming up against, and you were saying that that is infinite, and I would agree. But I would also point out it is in some sense. I think you're right. This is a little bit past 1 over x in some sense. But it's not a power function past 1 over x, which will be my next example. So power function is what? T to the p. You know, f of t equals t to the p. This is a power function. In contrast, this is not a power function, right? It's something else. But it is also something else whose integral diverges, like 1 over this. I mean, this diverges because this goes to infinity, right? What happens here? I see, yeah, so you're right. This piece right here, inside the absolute value, this piece goes to what? So you guys asked me last time, do we need to build a graph? And the answer is, yeah, I think you do, because otherwise how are you going to confidently know? I mean, this is how I know. Maybe you memorized all the limits, I don't know. I've just memorized the graphs. Like, I know what the functions look like, and because I know that, I can answer all these limits, okay? So when I think about the log of a going to 0 from the right, I think about this graph from going what? Negative infinity. But what happens to that negative infinity? Well, it's being fed to the absolute value, right? So then you're looking at log of infinity, which is, again, everything's infinity here. So this goes to infinity. But of course there's a minus outside, right? So we have this, and this, by the way, this is 0, right? Same over here, this is also 0. So what do we say about this integral? Does it go to infinity? Does it go to minus infinity? It's got both, right? And like I was telling you about last time, when there are two kinds of divergence in a problem, we do not link them and symmetrically approach both, right? The definition in Calculus 2 in standard mathematical discourse is when you have a doubly improper thing, you don't link the limits. I don't somehow try to make this and this go to 0 and this go to infinity in some kind of symmetrical way. They're just disconnected things that are going unbounded. So that piece is going to infinity. This piece is going to minus infinity. In this case, we say the limit does not exist, which I'll just write as equals dne, just because, well, you guys don't like to write the sentence, this integral does not exist because I have shown as such in the limiting process above. Like that, writing that whole sentence would be awful, yes. So many words. So I will allow you equals dne. Okay. As a shorthand for that sentence that, you know, yeah, go ahead.
Would it be possible to simplify it further? Those rules?
No. These are not indeterminate limits. You're looking at a log of infinity. You're looking at a log of something that's going to infinity. That's not indeterminate. It's just blowing up.
But the whole thing as a whole is negative.
And the reason that it's not of indeterminate type is these infinities are separate. They're not interlinked. Like you'd have to have both the infinity and the minus infinity part of a common limiting process in order to employ L'Hopital's rule and get some kind of cancellation. That won't happen here. Yeah.
So if that's one of the restrictions for using L'Hopital's rule, what are some of the other ones that we should know about?
Oh, restrictions for using L'Hopital's rule. Well, I think that's calculus 1. Like I don't know what to tell you right offhand. There are subtle examples, but I don't have them on tap, unfortunately. Hopefully that won't happen to us. We'll know it when it does. And that'll be the example that causes me to make an announcement later in the day when it happens. I feel like this is a prophecy, but it's always a prophecy. Not taking the bait just yet. Not taking the bait. It's Dr. Sprano trying to tempt me. Forbidden fruit over there. It's not an apple, it's a snake. Let's see here. No, it's probably harmless, but I have other things I want to tell you about today. So I'm going to resist the urge to do that unless we have time at the end. So let's get back to good question today. I think good question. I mean, let's talk about that power function I was talking about, though, because we'd like to have this as kind of a point of reference. All right. So here it is. I guess I'll call this a theorem. It's an example in my notes, I think, but this is the theorem. And we're going to just kind of present it this way. Integral from 1 to infinity of dx over x to the power p, all right, is convergent if and only if, well, I'll tell you what, I'll use one of these double arrow symbols for you guys. If and only if p is greater than 1. So, last class, what did we do? P equals 1, right? Integral from 1 to infinity of dx over x. We worked that. We found it was infinity, right? So we settled that one last class, right? You were just bouncing off that. Sam's question was bouncing off that. So let p not equal to 1, right? And notice that the integral from 1 to infinity of dx over x to the p is equal to the limit as t goes to infinity of the integral from 1 to t, all right? Let's rewrite that as x to the minus p dx, because that'll help us, yeah? And then what? What's the integral of x to the minus p? You guys know this. So we get x to the minus p plus 1 divided by minus p plus 1, right? We have to evaluate that from 1 to t. And let's see, let me work that out. So we got the limit as t goes to infinity. I'll rewrite this as, you know, sorry guys, let me just erase that for a second here. I want to pull the constant out of the limit, if that's okay with you guys. So I'm going to pull that 1 over 1 minus p out front. That's just a number. And then we're up against the limit as t goes to infinity of 1 over t to the p minus 1. Minus 1. Work out the algebra, see that I'm right, okay? Do you see it? So think about that limit. How does it go? How does this work out? It's equal to what? It's equal to 1 over 1 minus p if p is what? And it's equal to infinity if p is what? What does it take for this 1 over t to the p minus 1 term to go to 0? For what? P greater than 1. We need p to be greater than 1. That makes this a positive power. In the denominator, that goes to a really big number, hence the ratio goes to a really small number. And as that means, oh man, look at that. Come on. I got a minus 1 here, right? My point was that this piece goes to 0, which leaves you this minus 1, right? So I'm missing a minus here, aren't I? But to be nicer, I'm going to rewrite that as p minus 1, just to have less minuses in my formula. Yes, sir? I saw a hand.
Oh, yeah. I was just going to say if p is greater than 1, that coefficient is going to be negative.
Yes. Yeah. That's very true. And that's also, and that, why is that relevant? Because what are we expecting here? What is this we're calculating? We're calculating the area, right? 1 over x to the p, what's that look like? Roughly speaking, like this, right? I mean, up to the limits of my artistry, this is the graph, you know? Well, that's if p is positive, I suppose. If p is negative, then something else, right? Like if I put p equals to minus a half, this is the square root function, right? What's the graph of that look like? Well, like this, right? Not, it shouldn't bow back down, okay? But anyway, my point is for the interesting cases, I should say, p greater than 0, right? For p greater than 0, the graph, roughly speaking, looks like that. And what are we doing? Well, we're calculating the area from where to where? From 1 to infinity, right? If it's bounded. And the answer is, well, sometimes, right? Sometimes. So this area is, in fact, equal to 1 over p minus 1 if p is, like we were just saying, greater than 1, right? And what happens if p is less than, if p is less than 1, then what happens? Then that makes, if p is less than 1, then 1 over t to the p minus 1 is actually equal to t to the 1 minus p, right? Where 1 minus p is, in fact, a positive power. And t to a positive power goes to infinity as t goes to infinity. Consequently, that integral diverges in the case p is Less than 1. Yeah.
So where exactly did you get the negative p plus 1 from?
Negative p plus 1. I integrated. It's just integral of, x to the n dx is, yeah, nothing fancy.
Because p is a constant.
Yeah, I'm just n equals to minus p is all. Just the usual power law for integration. Mm-hmm. Yeah.
I have a question. Back on this board, why did you put a equals 0 to the right if we're integrating from 1 to infinity?
Oh, that's a good question. I think we should have... Yeah, that's a very good question. How do we fix it? Did you already... I think we're done over there. I think you can come back over here now. Oh, you already did. Cool. So it's just this. And, well, that may change the answer, though. I got to think through this. What happens? This no longer goes to infinity, does it? If we're going to 1 from the right, what happens to the log? Log of 1 is 0, right? So we're feeding 0, a small positive number, into this. All right? So what that means is that altogether this goes to minus infinity. But there's a minus. Minus minus is plus. So the net result of this is that it's not a non-existent limit. It is a what? It's infinity. Yeah, because when both pieces grow without bound, infinity plus infinity still gives you infinity. That is true. Infinity minus infinity, we have to say, does not exist. Unless the infinities are linked through a common limiting process, in which case it's indeterminate and we can further reduce it, hopefully. This I could have anticipated if I thought about the graph of this, right? Because the graph of 1 over x log x, what's it look like? I'm not looking for anything terribly highbrow here, but think about it. Yeah, it has a vertical asymptote, right? At x equal to 1, right? But the larger point is log x and x are both what? Positive. Which means that the graph of this, I don't really care. Funky stuff happens over here, right? I don't care, whatever. But the part we're interested in, this looks like that. So you're calculating the area bounded under the red curve. It can't be non-exists, right? There's nothing to cancel there. It's all positive area. So we should have expected to get infinity if we had just kind of did a gut check on the graph, which I didn't do. My bad. So thank you for your question. Very helpful. In a weaker section of Calculus 2, I would have either never found out about this or thought about it tonight when somebody sent me an email, and then I was like, dope! Or worse. So anyway, it's very, students are important. Like, I'll tell you what. Very helpful. Thank you. Other questions? Or corrections? Yeah.
I know this is kind of awful what we're walking around now, but
Yeah.
I'm still confused about the recursive formulas.
The recursive formulas. Yeah. Well, we'll get back to those another day, I think, because, like you said, I think that's a little bit off the beaten track here for the moment. So, but we can come back. Yep. Attendance. Yowzers. Yeah, this is a 2 for 2 because I forgot to do it yesterday, right? So you check 2 boxes. Here you go. All right. So, listen. This is, I say it's a theorem, and the reason I say this is a theorem is because this is something we need to remember. All right? Now, I don't usually find myself saying in Calculus 2, this is a theorem you need to be able to prove because you're Calculus 2 students, right? But hey, this is a theorem you need to be able to prove because the proof is essentially easy homework problems, right? Like this is something that you can prove. We just went through the proof. It's just that, okay? But besides that, I just need you to remember it. And the reason I need you to remember it is it's a point of reference. And you say, well, what does that help us? Let me show you how it helps you. Let's try our hand at something. Example, where am I on? Oh, I don't know. 4? Where are you? I've lost track. Suppose you're up against the integral, say, from 1 to infinity of, oh, I don't know, dx over x to the 5th plus 7. And you're asked to decide, does this integral converge or diverge? And I don't guess I've defined those words carefully, but what I mean by converge or diverge, by converge I mean that the limiting process which we implicitly intend with that notation, do those limits exist and are they finite numbers? All right. Diverge means that the limits involved in the integration process, well, they go badly and they blow up or they don't exist. All right. Okay. So what do you guys think? Do you guys remember when we integrated 1 over x to the 5th plus 7? Do you guys know how to integrate 1 over x to the 5th plus 7? How would you do it? Calculus? I mean, I guess I could do it. But I shouldn't show you how. We need complex analysis, really. You could use the what are called the 5th roots of unity. You could do a partial fractions decomposition of this into 5 terms. But the calculation would be complex. We don't want to do that, right? OK, so how do we decide whether this converges or check out this. 1 over x to the 5th plus 7, right? Is it positive? Well, yeah, right? Well, that's not clear, is it? Context, right? If x is greater than or equal to 1, let's say. If x is greater than or equal to 1, that's definitely positive, right? Is this reasonable? Is this less than 1 over x to the power 5? What have I done? I just did what? I made the denominator smaller, right? See that? And then the theorem is this: integral from 1 to infinity of dx over x to the 5th plus 7 is less than the integral from 1 to infinity of dx over x to the power 5, which, by the way, is equal to what? No. It's 1 over 5 minus 1. P equals 5. Now, logically, that implies that, yes, this integral converges. Because it's smaller, right? It's smaller than an integral which converges. So if we have the integral of a positive thing, right, and you can compare it to a larger function whose integral over the same domain converges, it then follows that that integral to which you're looking at converges. And not just that, that the you also get that the integral of this thing that we don't want to actually integrate, it's between 0 and a quarter. The value of the integral is like that. So this theorem I'm telling you about is called the comparison theorem. We can compare a given improper integral to something which is a reference point, right? So these integral of the p power functions are a nice reference point because it's kind of not too hard to come up with things like this, yeah. Does this make sense? Yep.
I'm confused how you're evaluating the integral of 1 over x to the 5.
I'm using the theorem. We just worked out that 1 over integral from 1 to infinity of 1 over x to the p is equal to 1 over p minus 1 in the case that p is greater than 1. Well, we're in the p equals 5 case, so 1 over 5 minus 1 is 1 over 4. It's just that. Now, hey, if you don't remember the theorem, you can work it back out again, right? Fair enough. Yep.
I might have missed this, but where did you get the 5 from? Was that because of the exponent, or?
Yeah, the exponent. It's this 5 here. Yeah.
So like if x was less than 1 and you had like a negative number in the denominator, then it's like so it'd be infinity then? Or
You want me to do yeah, let's do another example. So if I had something like, and I'm going to get into trouble here. I'm sure I'll get into trouble. Doubtless I'll get into trouble here. Let me try though. Integral of, oh, yowzers. Dx over, oh. It's just a mental block I have. I have a hard time coming up with ones that diverge, that are interesting. Let's see here. X, let's say 2x minus sine squared x. I reserve the right to give up on this example if I've written down an impossible example, okay? I think this is going to be interesting for us. What's the situation here? If x is greater than 1, then 2x is greater than or equal to 2, right? And 2x minus sine of x squared, sine squared x, is greater than or equal to 1, right? How do I know that? How big is sine? In magnitude, at most 1, right? So if you subtract the sine squared, worst thing that can happen to you is you're subtracting 1. Consequently, the denominator, at least it's not 0, right? We're integrating something where the denominator is at its smallest, you know, just 2x. So I think we have the following inequality. 1 over 2x minus sine squared x is what? I believe that is greater than? Yeah, greater than 1 over 2x. Why is that? On the left-hand side, yeah.
Because if you're subtracting sine squared x, subtracting an x1.
Right, because I'm subtracting a positive thing, right? Also, like I'd be a little bit more wary about this if I had sine x. I would have gotten into trouble because then sine is sometimes positive, sometimes negative. It's a real hassle. Yeah. But with sine squared, I know it's positive. I'm subtracting a positive number, so that makes this denominator smaller than that denominator, which makes the fraction larger. So we have this comparison. Yeah.
Does sine squared x ever equal 0?
It does. Sorry. There you go. Thank you. Good point. That is a legit point right there. Thank you. And but these comparison tests are still true. Like you can go back in here and adorn this with equals if you want. It's just not actually realized. Okay, then what? Well, then we have the integral from 1 to infinity of dx over 2x minus sine squared x diverges, since the integral from dx over x from 1 to infinity diverges. And that implies that 1/2 times the integral from 1 to infinity of dx over x diverges. So this is a theorem that I should probably mention to you. If we have an integral which diverges, any constant multiple of it also diverges. Okay, so if I have like a p, if the integral of 1 over x diverges, well, if you multiply it by 2, it still diverges. If you multiply it by 1/2, it still diverges. So this is 1/2 the p equals 1 integral. And why does this give you a divergence of this? Because you've got, basically you can just think about integrating this inequality. And the thing is, the definite integral, it preserves inequalities, just like this. Right? And so if this smaller thing blows up to infinity, then the integral which is bigger than that must also blow up to infinity. This is the other side of the comparison test. Does that make sense? So there's a couple problems like this in your homework to try to help you to, process this idea. This is, so like this course, there's a few main story arcs. Like the first story arc is integration. You're in the middle of it. You're near the end. Not quite though, because after test 1, we study differential equations. How do you solve differential equations? For the most part, separate and integrate. So we're right back to integration again, right? Bunch of integration after test 1 still. Okay? Then, once you get to the end of integration, then there's a dramatic change of scenery in here. We start studying sequences and series. Sequences, relatively benign. Those are just functions of natural numbers. And you're only looking at limits that go to infinity, fine. But then we start looking at series. Series are when you take a sequence and you start adding up terms. When we get to series, there's like a dozen theorems that we use to study the convergence and divergence of numerical series. This idea of comparison comes back there with a vengeance. It's one of our main tools of investigation. So that's part of the reason I think it's important to spend a little bit of time here on this, because it sort of seeds your mind, prepares the way for that making more sense to you later. And anyway, and also there's just integrals, improper integrals, that this is the way you have to think about them, because you can't just directly integrate everything, right? I mean, there's certain things we can integrate, there's certain things we can't. And for the things that we can't, many of them are close enough to be compared to something that we can, so it's still a win, right? We still have something to say about that diverging. Does that make sense? Now you might ask, what's the application of improper integrals? Yeah?
So just to make sure,
Uh-huh.
the integral from 1 to infinity of dx over x to p always converges when p is greater than 1, and it always diverges when p is 1 or less.
Yes. So so what I should say is this. What's the definition of divergence? It's divergent. No, more basic. It's divergent if it's not convergent. So when I say that this is convergent if and only if p is greater than 1, that means if it's not greater than 1, it's divergent, which is what you're saying. So less than or equal to 1, less than or equal to 1 gives us a divergent integral. Some of those are obvious, right? Like p equals minus 1/2. You're integrating the square root from 1 to infinity. Does that diverge? Well, yes, of course, right? The area under the square root functions, half the area under a parabola turns sideways forever and ever. That's divergent, right? But the 1 over x function, it gives you false hope, because it's going to 0. You think maybe the integral converges, but we saw last time it doesn't. So, There's one major application to this I want to talk about today, which is statistics. Well, probability, really. Do you guys like probability? Yes, no, maybe so? Just a little bit.
How much were you betting?
How much are we betting? I'll allow it. All right. Definition. Definition. F of f, a function from the reals to the reals, where, I mean, I could replace this r with, say, 0 to infinity. In other words, I'm saying f of x is non-negative, right? F of x is greater than or equal to 0 for all x in the reals, such that the integral from minus infinity to infinity of f of x dx is equal to 1 is called a probability distribution. So this makes for fun applied problems about improper integration, because you can do things like give students a partially defined potential probability distribution and then say, you guys turn the screws and adjust it so it becomes an honest to goodness probability distribution, right? How do you use, what does this have to do with probability? Well, like, the application is, if you want the probability that, say x is between between a and b, like this, you just integrate the probability distribution from a to b, and that gives you the probability. So that's why we call it a probability distribution. If you integrate the probability over some finite range of values, that gives you the probability that x is measured to be in that range. So, yep.
So basically, you're saying x can be negative infinity to infinity, but the function itself has to be positive?
Yeah. Well, non-negative. Could be 0.
Right, non-negative. And then all the area under the curve is 1 because that's
Some of the, yeah.
probability works.
Yeah, we're not in the sports. We don't say we can give 110%. Like, there's just 100% probability,
Okay.
For example, f of x equals to 0 if x is less than or equal to, less than 0. And let's say a e to the minus x if x is greater than or equal to 0. Just to make it slightly more interesting, let me throw a 2 in here. All right. Question: for what choice of A is this a probability distribution? Okay, so we need to integrate. So first of all, as long as A is what? As long as A is positive, we're okay on the condition that the function's non-negative, okay? So check that box. So if A is greater than 0, then f of x is greater than or equal to 0. So check that box. Okay, great. So what we want to calculate is the integral from minus infinity to infinity of f of x dx, right? And my point to you is we break that up into two pieces, like from minus infinity to 0, and then from 0 to infinity, yeah? But one of these is not like the other. One of these does not belong. I mean, it belongs, but it's 0. Or as my friend Tipomoy Guhar Sarkar would say, Jiro. Let's see here. I miss Tipomoy. That was hilarious. So that goes to 0, like so, because the function's 0 over that whole, right, by definition, 0. The other one, we're up against what? The limit as t goes to infinity of what? the integral from 0 to t